Okay, in this first problem, what we're asked to do is find the initial position of the particle and the position at time t equals 2. And since we're given the position function right there, what we can do to find the initial position, which is when t equals 0, is just plug in these time values into the position function given to us in the problem up here. So what I'm going to do is find what x of 0 would end up being, and by plugging in t equals 0 into it, I will end up with 0. So the position of the particle at time 0 is 0. So the particle's at 0 feet when we first start counting time. And then for time 2, I'm going to plug 2 into my position, and what we'll end up with that is, let's see, 2 cubed is 8, and then 8 minus 2 squared is 4 times 6 is 24, and then plus 9 times 2 is 18. So 8 minus 24 is 16, negative 16, excuse me, and then negative 16 plus 18 is 2. So at time 2, the particle is at position 2 feet. And then because I am a detailed person, I like to put the units on these, so 0 feet and 2 feet. Okay, all right, question B is asking us to find the initial velocity of the particle and the velocity at t equals 2 seconds, and then explain what each one means about the direction of motion of the particle. So when we're asked about the velocity of the particle and we're given position, I want you guys to understand that finding the velocity means taking the derivative of position. So what we're going to do to find the velocity is start by taking the derivative of our initial position function up there. So that gives us 3t squared minus 12t plus 9. And then what we can do for the initial velocity is plug in 0 into it, and we get 9 feet per second. And the velocity at time 2 gives us, let's see, that would be 3 times 4 minus 12 times 2 is 24 plus 9. So that's 12 minus 24 is negative 12. Negative 12 plus 9 is negative 3. So negative 3 feet per second. And then what that number means, the 9 feet per second, is because it's positive, the particle is moving towards the right. So at time 0, the particle is actively moving to the right of the number line. And then for this velocity right there, because the velocity is negative, that means that at time 2, the particle is moving to the left. In question C, we're asked to find, again, the acceleration and the acceleration at 2 seconds. So the acceleration of the particle is the derivative of velocity. So we're going to find that right here. So that gives us 6t minus 12. And the initial acceleration is negative 12. The units on that are feet per second. And then the acceleration at time 2 is 0 feet per second. So that negative acceleration means that the velocity is decreasing, and that 0 feet per second means that the velocity is neither increasing or decreasing. The velocity of the particle isn't changing at time 2 seconds. At time 0 seconds, though, the velocity of the particle is decreasing, actively going down. Okay. Next part asks us to find the average velocity of the particle. So the average velocity is found by looking at the average rate of change of the position. So from 0 to 3, what we're going to do is find the position of the particle at time 3, the position of the particle at time 0, and then put them into this difference quotient here. Find the difference in positions, so the position at 3 minus the position at 0, and then divide it by 3 minus 0. So if you plug 3 into the position function up at the top, you get 0. You get 0 for the position, and then if you plug in 0 again into the position function, you get 0 as well. So 0 minus 0 divided by 3. We get the particle is changing approximately 0 feet over these 3 seconds. So the particle's average rate of change, average velocity, is 0 feet per second. And what that means is that over these 3 seconds, a particle on average is moving 0 feet per second. That does not mean that at every point in time the particle is moving at 0 feet per second, but what it means instead is that for some of this interval 0 to 3, the particle is moving with a positive velocity, and for some of the interval 0 to 3, the particle is moving with a negative velocity. And they average out in such a way to be 0 feet per second in the end. So over that 3 seconds from 0 to 3, the average velocity is 0. Now moving on to part E, during what time intervals is the particle moving to the right and to the left? What we're going to want to do is take our velocity function that we did before, and we've got v of t equals 3t squared minus 12t plus 9. And we're going to want to check for where the velocity is positive and also check for where the velocity is negative. So we will take our velocity, set it equal to 0, and just start factoring. So let's pull out a 3. We get t squared minus 4t plus 3, and we keep factoring. And this gives us two t values, t equals 1 and t equals 3. And from there, what we can do is make our sign chart. I'm going to label it v, and then put a bracket down so that I don't try testing any points that are less than t equals 0. Okay, so let's put t equals 1 and t equals 3 on our sign chart. And let's make some test points. So maybe if I test 0.5, and maybe over here if I test 2, and here if I test 4. So if I plug 0.5 into my velocity, so 3 is positive, 0.5 minus 1 is negative, 0.5 minus 3 is negative, so we got a positive times a negative times a negative, and that would end up as positive. At 1, the velocity is 0, and then if I plug 2 in, I'll get positive, and then positive, and then negative, so that will end up being negative velocities between those, with a 0 velocity at 3. And if you test 4, you'll end up with positive velocities. So what that means is that the particle is heading to the right over the time interval 0 to 1, and, so that symbol means union or and, the time interval 3 to infinity. And the particle is heading to the left over the time interval 1 to 3. Because particle is heading to the right because the velocity is positive. And for the left, particle is heading left. We know that because the velocity is negative. Okay, on to the next one. Okay, so in problem number 2, we're asked again about a particle moving along a horizontal line according to this position function right there, where x is in feet and t is in seconds, and then we're only worried about positive times. Okay, so the first thing asks us to find the velocity of the particle at time 3. So to find the velocity from the position, we are going to jump right into our derivative. So let's find the derivative of the position function. And the derivative of this function up here will use the product rule and a chain rule. The chain rule because of the derivative of t minus 2 cubed. So let's start out with the product rule. So I'm going to take the derivative of my u and keep the v the same. So the derivative of the u uses the chain rule. I'm going to have 1 as the derivative of the inside times 3, and then t minus 2 squared. And then I'm going to keep my v the same. plus, and now the other side of my product rule. I'm going to keep my u the same and multiply by the derivative of v, which is just 1. So this velocity function is better written as 3 times t minus 2 squared times t minus 5 plus t minus 2 cubed. There's my velocity. Okay, that asks us to find the velocity at time 3. So the velocity at time 3 is found by just plugging 3 into the velocity equation there. That's going to give us 3 times 1 squared times negative 2 plus, and then 1 cubed. So this whole thing will end up turning into, let's see, 3 times negative 2 is negative 6. Negative 6 plus 1 is negative 5. So negative 5 feet per second. And that means that the particle is moving to the left at a rate of 5 feet per second. Okay. What we're asked to do next is find the average velocity of the particle over that interval 0 to 3. So the average velocity asks us to look at the rate of change of position over that time interval. So we're going to set up a slope equation from 0 to 3 and look at the rate of change over that span of time. So the position at time 3 is negative 2. You can get that by just plugging 3 into the position function up there. 3 minus 2 is 1. Cubed is still 1. 3 minus 5 is negative 2. Minus, and then if we plug 0 into the position function, we get negative 2 cubed, which is negative 8. And then negative 8 times negative 5 would give us positive 40 over 3 minus 0. So this average velocity will turn into negative 42 divided by 3, which is equal to negative 14 feet per second. So what this means is that this is the velocity on average over 0 to 3 seconds. Whereas this up here is the velocity at time 3 seconds. So that velocity right there typically means that on average the particle is going negative 14 feet per second over this time interval. There was probably some spots where it was moving faster than that and probably some spots where it was moving slower than that. Whereas this is saying that at time t equals 3 the particle is moving exactly negative 5 feet per second. So this number is over a span of time. This number is at a moment in time. Okay. On to the next one. During what time intervals is the particle moving to the right or to the left? What we're going to do is the same as we did in the previous problem. We're going to take our velocity function, which I'm just going to copy down right here for you, is 3 t minus 2 squared times t minus 5 plus t minus 2 cubed. And then what we're going to do is factor this. This is kind of a tricky algebraic maneuver. What we're going to do is factor out from this term a t minus 2 squared, and we're also going to factor out a t minus 2 squared from that term right there. Both of these have a t minus 2 squared that we can pull out. So I'm going to do that. Take out a t minus 2 squared, and I'm going to write left over. We've got a 3 left over from the first term, and also a t minus 5 left over. And from the second term, I took out a t minus 2 squared, so that just leaves a single t minus 2. And then I'm going to simplify this a little bit. T minus 2 squared. And then if I distribute the 3 and combine some like terms, we get 3t plus 1t. That would make 4t And then 3 times negative 5 is negative 15. Negative 15 minus 2 is negative 17. So 4t minus 17 left over. And what that means is that our two time intervals, points in time for where the particle is moving with 0 as a velocity is t equals 2 and t equals 17 fourths, which is approximately 4.25. We're going to set up a sign chart. I'm going to put a bracket at time 0, because we don't need to worry about anything that's less than 0. And then I'm going to put my two important points on there, 2 and 4.25. And then let's just test some points from that. I can plug in 1 into my velocity to test that. 1 minus 2 is negative, squared is positive. And then when we plug 1 into this factor right there, we get a negative. So a positive times a negative is a negative. At 2, the velocity is 0. And then if I plug in a number between these right there, say at 3, I plug 3 into t minus 2, we get 1. We square it, it's positive. And if I plug 3 into 4t minus 17, I get 4 times 3 is 12. Minus 17 is negative, so a positive times a negative is another negative. Velocity is 0 at 4.25. And if we plug in one more test point into our velocity, let's say 5. 5 minus 2 is positive, squared is positive. Then 4 times 5 is 20, minus 17 is positive. So the velocity is positive on that time interval. So what we've got here is the particles moving to the right over the time interval 4.25 to infinity, and the particles moving to the left from 0 to 2 and from 2 to 4.25. What happens is the particle briefly stops after 2 seconds, but then keeps moving to the left for a little bit after that. All right, so for this last problem on the back part of the first page, we're given again a position function with time greater than 0, and in part A, we're asked to find the velocity at time 1. So what we're going to do is jump straight into the derivative of the position function. We get 3t squared minus 12t plus 9. And if I plug 1 into that particular velocity, we get 3 minus 12 plus 9. 3 minus 12 is negative 9. Negative 9 plus 9 is 0 feet per second. And what this means is that the particle is at rest. For a brief moment, the particle is not moving. That doesn't mean that it doesn't ever move. It just means that at time t equals 1, the particle isn't moving. Okay, next question. At what time interval is the particle moving to the right, to the left? We can approach this in much the same way as we did in the other ones. As a matter of fact, I think this might actually be very similar to the first one. So we're just going to approach it like that. I'm going to factor out a 3. And then factor completely. So t squared minus 4t plus 3 can factor into t minus 3 and t minus 1. And then we get t equals 3 and t equals 1 as our important points. So just confirming that we can still use a sign chart to find when the particle is moving to the right and to the left. We slap 1 on the time and 3 on the time. Velocity is 0 at both of those points, and we can plug in some test points into that. Say 0.5, 2, and 4. And if you plug those test points into the velocity, what you'll find is that the velocity is going from positive to negative to positive again. So what that means is that the particle is moving to the right from 0 to 1 and 3 to infinity. And the particle is moving left from 1 to 3. Because the velocity is positive, and then the velocity is negative at each of those intervals, respectively. Our last question here gets a little bit more interesting. So we are asked to find the velocity of the particle at time t equals 2. So let's find that pretty quickly. The velocity at time 2, if we plug 2 into our velocity, say, up here, gives us 3 times negative 1 times, and then positive 1. So that gives us a value of negative 3. And it also asks us to find the acceleration of the particle at time t equals 2. Remember, I asked you to change this time to t equals 2, not t equals 1. So what we need to do is take our velocity and find the acceleration from the velocity. So I'm going to do that work over here. My original velocity function was 3t squared minus 12t plus 9. This is before I started factoring it. So let's take the velocity and find its derivative to get acceleration. 6t minus 12. Okay? And then plugging in 2 into the acceleration means that we get an acceleration of 0. Now this is actually really interesting for this problem because it's kind of unexpected. What we expected to have happen was the acceleration be either positive or negative. And if the acceleration was positive, that would mean the velocity is increasing. If the acceleration was negative, that would mean the velocity is decreasing. However, because the acceleration is 0, what this means is that the velocity is neither increasing or decreasing. And because the acceleration is 0, that also means that the speed is neither increasing nor decreasing. Remember that if a particle has both positive velocity and positive acceleration, that means that the particle is speeding up. And if the velocity is negative and the acceleration is negative, that means the particle is slowing down, that means the particle is also speeding up. Almost had that backwards. But only if the velocity is positive and the acceleration is negative, or if the velocity is negative and the acceleration is positive. So if there are different signs, that means that the particle is slowing down. However, in this case, because the acceleration is 0, none of this really applies. It means that the velocity is neither increasing or decreasing, and the speed is neither increasing or decreasing either. The particle is just at a maximum or minimum velocity. On this page, we see a bunch of problems that are all calculator active. And what that means is that you can feel free to use your calculator to analyze these in any particular way that you think would be useful. We're going to chiefly use our calculator to analyze these by graphing things like the velocity or the acceleration to help us make our sign charts and make our conclusions. So if we start in part A, we want to find the instantaneous velocity when t equals 2. So what we should start by doing is start by finding the velocity function, which is the derivative of position. So we've got negative 3 t squared plus 14 t minus 14. And then what we're going to do is just plug in 2 for the time and see what the velocity at times 2 is. And then if you go through and plug in 2 into this velocity equation right there, what you should end up with is that the velocity is 22 meters per second. Okay, so this means that the particle is heading towards the right at that particular point in time. I just like to say that so that I just kind of have a vision in my head of at time 2, a particle moving towards the right at this particular velocity, 22 meters per second. Okay, so for the next one, we're going to find the acceleration of the particle. So I'm going to want to go one level lower and find the acceleration function by taking the derivative of velocity. So we're going to end up with negative 6t plus 14. And then if I find the acceleration at time 2, we end up with negative 12 plus 14, which is 2 meters per second. Okay, so the acceleration is 2 meters per second. And because acceleration and velocity are both positive numbers, they're both heading towards the right, what that means my particle is doing is that the particle is speeding up. Because both velocity and acceleration have the same sign. If they had different signs, say one was positive, one was negative, that would signify that the particle's slowing down. And if they were both negative, that would mean that the particle is speeding up, just speeding up to the left-hand direction. Okay, so for this last part, part C, what we want to know is where's the particle at rest, when is the particle moving to the right, and when's the particle moving to the left. Now you're going to be very tempted to just take your velocity equation up here and make a sign chart for the velocity equation, because as we've seen up until now, the velocity, a particle is heading to the right when its velocity is positive, and a particle is heading to the left when its velocity is negative. And yes, we will sort of be thinking about a sign chart for this velocity function up there, but that thing is not especially factorable. So what I'm going to ask you to do is to reach for your calculator right now and graph velocity in your calculator in a standard 10 by 10 by 10 window. And you should end up seeing a graph that looks a little bit like this. So what we've got is a parabola that looks like it crosses the x-axis at 2 separate places right there. And remember, this is the graph of velocity, so I'm going to label right next to this parabola that this is the graph of velocity. And I'm going to actually use this to make my sign chart from here. So according to my velocity graph, after 0, we've got a couple places where the velocity is literally 0. The velocity is literally 0 at this point right there. And if you go into your calculator and do second calc 0, you will find that that particular 0 is 1.451. And if you do the same for the other 0, you'll find that the velocity is 0 when t equals 3.215. So these are both of my 2 time values for which the velocity is 0. Or when the particle is at rest. So the particle is at rest at both of those times. And then what we can do is we can look closer at my velocity graph over here and try to figure out where the velocity is positive and where the velocity is negative in relation to both of those 2 times. So as you can see, in between those 2 times, my velocity graph is literally above the x-axis, so my velocity is positive in that interval. And then before the first rest time, the velocity graph is below the x-axis, so the velocity is negative before that first time. And after that second point in time, my velocity graph is negative. It's below the x-axis, lives in negative land, so my velocity is negative after that. What we're basically doing here is examining this graph for places where the graph is literally positive and literally negative, just like we examined graphs of f prime before to find where the intervals of the function were increasing or decreasing. Except here it's velocity, and we want to know where the particle is going to the right, going to the left, instead of increasing and decreasing. So according to this graph and according to this sign chart, we end up with a few intervals here. So we've got that the particle is moving to the right on the interval 1.451 to 3.215, and the particle is moving to the left on the interval 0 to 1.451 and the interval 3.215 to infinity. And again, because the velocity is literally positive in this space, the particle is moving to the right. And because the velocity is literally negative in these two spaces, we say that the particle is moving to the left. All right, on to the next question, number 5. So what we're given is the position of a particle at any time t seconds, again, with t greater than 0, and we're given this function right there. I'm going to write it down slightly bigger in the space given. So the position s of t equals t squared minus sine of t. And then it gives us a specific interval of time from 0 to 3. And then t is measured in seconds and s is measured in meters. And what we're being asked to do here is find the acceleration of the particle at each moment in time the velocity of the particle is 0. So the first thing we should do is find the velocity of the particle. The velocity of the particle is found by, again, taking the derivative of position. So let's go ahead and find the derivative of this position function. The derivative of t squared is 2t minus cosine of t. And then if we want to find where the velocity is equal to 0, we can consider where the velocity is equal to 0. Now this is really, really difficult to solve by hand. And that's where this calculator active thing comes into play. What we're going to do is graph that function in our calculator and then look for zeros. Okay, so what I did is I entered my velocity function into my calculator and I graphed it only on the window from 0 to 3, because I know according to this interval that I only need to worry about times that are between 0 and 3. So I graphed my function in my calculator, and hopefully you did as well, and what I got was a line that looks roughly like this. All right, now once I have that graph in front of me, what I can do is I can use the second calc menu in my calculator to look for this 0 right there. So I'm going to do second calc 0, and I'm going to go just to the left of the 0 and just to the right of the 0 and bound it. And then if you hit enter again, you will get that this 0 is at t equals 0.4501. is what we'll say. T equals 0.4501. Okay, so that's where my 0 is. This is where the particle is at rest, because that's where the velocity is equal to 0. So that is when the particle is at rest, where the velocity is 0. And what we want to do is find what the acceleration of the particle is at that point in time. Now, the acceleration of the particle is found by looking at the derivative of velocity. So when we find the acceleration, what we're actually doing here is looking at the slope at that particular point. So let's go in and let's use our derivative knowledge and find what the acceleration would be. So from this velocity equation, I'm going to derive that over here on this side and find what my acceleration would be. The derivative of 2t is 2. And then the derivative of cosine is negative sine. So we have minus negative sine, which would be positive sine of t. And then I want to figure out what the acceleration would be at that particular point in time. So I'm just going to plug in 0.4501 into my acceleration and see what we get. Okay, and if I use a little bit of prediction here, this slope is a positive slope, so hopefully this means that my acceleration should be positive, some positive number, after I plug in 0.4501 in for my t. So let's see. So acceleration at 0.4501 would be equal to, so 2 plus sine of 0.4501, and we get 2.435. Okay, so there's my acceleration. I'm going to tag a unit on it. It's meters per second, because acceleration is the rate of change of velocity, meters per second. Okay, on to the next one. In this particular question, it's doubly important to take notice of what we are being given here. So we are being given not the particle's position function, but the particle's velocity function. We're given it right there. V of t equals cosine of t squared plus t. I'm going to write it right down here. And we're also given a certain time interval to look at from 0 to 2. And it looks like we've got meters per second and seconds again. Okay, so find the velocity of the particle each time the acceleration is 0. Okay, no problem. That means that we need to look at the acceleration of the particle. The acceleration is the derivative of velocity, so let's look there. In order to derive this velocity here, I see cosine of t squared. So we've got a chain rule situation with an inside and an outside. The derivative of the inside layer is 2t. The derivative of the outside, with the inside kept the same, is negative sine of t squared. And then the derivative of the t is just 1. So all told, the acceleration function would be equal to negative 2t sine of t squared plus 1. And we want to know when the acceleration is equal to 0. So let's graph this in our calculators and take a look. Okay, so if you've graphed this in your calculator, you should see a window, and hopefully what you've done is restricted your window to be only from 0 to 2. And then kind of adjusted your y values so that you can get a good clear picture of what this curve is doing. And on my side, what I see is a curve that kind of looks like this. Goes down and then back up, so something like that. And we see two different times where this acceleration curve is equal to 0. So I see that the acceleration is equal to 0 right there, and the acceleration is also equal to 0 at that point right there. So what I want to do is find these time values, again, by using second calc 0, and then going through the left bound and the right bound to find those time values. So let's take a look. Okay, after going through and doing the second calc values, it looks like my first time value is t equals 0.813, and my second time value is t equals 1.685. So these are both places where the acceleration is equal to 0. Okay, and then what the problem wants us to do is find the velocity of the particle at each of these two times. So let's take our velocity, which is, again, v of t equals cosine of t squared plus t. Let's plug each of these times into it. So then our velocity at 0.813 would end up being, the velocity of 0.813 would end up being 1.602 meters per second, and then the velocity at time 1.685 would end up being 0.7304 meters per second. Okay, there we go. Let's go on to the next one. All right, this next problem looks very much different than all the other ones, and that's because it almost certainly is. We're not given a position function. We're not even really given any function. What we're given is a graph. And the first thing that I want you to notice, both in reading the problem and also in just looking at it, is that this graph is the graph of velocity. This is a velocity graph. And that is going to tell us certain things easier than others as we go in and answer these questions. So we'll have to think hard and make sure that we know what level of graph we're looking at and whether or not this graph is being used to answer the question in the right way. Okay, so the graph above shows the velocity in miles per hour of a particle moving along the x-axis, just a line from 0 to 11 hours. We've got a semicircle and two line segments. And then part A asks, from 0 to 11 hours, when is the speed of the particle the greatest? Now, the speed of a particle is the velocity without caring about direction. So we don't especially care whether the particle is moving to the right or moving to the left. All we care about is what's the absolute fastest the particle is moving at. And how I want to kind of guide you through this is think about what the speed would be at this particular point in time, right there. So at t equals 2, it looks like my speed would be 2 miles per hour because the velocity at that point in time is positive 2. And because speed doesn't care about the positivity, we say just 2 miles per hour. Similarly, at time 5, it looks like my speed would be about 1 mile per hour. The velocity is about -1, but that only means that the particle is just moving to the left at a speed of 1 mile per hour. Similarly, at t equals 7, looks like my speed would be 5 miles per hour. My velocity is 5 miles per hour to the left, but my speed is just 5 miles per hour. So then with that in mind, the speed of the particle is the greatest probably at the point where, whether you care about positive or negative, just you have the sheer largest number. We're looking for where the absolute value of the velocity is the largest. And that occurs at one specific time value. It occurs way over here. Looks like at t equals 8. This is the spot where the velocity looks like -6. I don't see any other spots where the velocity is bigger than +6 or goes lower than -6. So this is where the greatest speed happens. So I'll say that happens at time t equals 6. The velocity right there is -6. So the speed is just +6. Because again, the -6 means that the particle is moving to the left. Okay, let's go on to the next piece. It asks at which of the times t equals 2, t equals 6, or t equals 9 hours is the acceleration of the particle the greatest. So the acceleration of a particle is found by looking at the derivative of velocity. Or in other words, the slope of velocity. So if we're wondering about acceleration in this problem, we want to look at the slope of velocity. And that's especially important for this graph because this is the graph of velocity. So at each of these 3 times, we'll want to look at the slope of the graph at that particular point. So let's take a look at t equals 2. At t equals 2, looks like we have a slope of 0. So I would say that at t equals 2, my acceleration, which is the slope of velocity, would be 0. At t equals 6, I would say that my acceleration, which again is the slope of velocity, let's take a look. At t equals 6, we are at that point right there. Okay, so we're looking for the slope of this line. Let's go in and calculate it. This point right there is, it looks like 8, comma, negative 6. And this point right there is 4, comma, 0. So we can use those 2 points to find the slope of this line that's connecting them. So let's do that. The slope between those 2 points would be negative 6 minus 0 over 8 minus 4. I'm just using y2 minus y1 over x2 minus x1 there. So we get negative 6 over 4. So negative 3/2. So it looks like my acceleration there would be negative 3/2, or negative 1.5. And let's look at the last acceleration, the acceleration at 9 hours. So the acceleration at 9 hours is again the slope of the velocity at t equals 9. And then what we're going to do is go ahead and look at that particular spot on the graph. So t equals 9 is right there. So let's look at that spot on the graph. And then we're looking for that slope. So this slope looks like it connects the points 8, negative 6, and this point right there, which is 10, comma, 0. So let's find the slope between those. We would have 0 minus negative 6 over 10 minus 8. So this would end up being positive 6 over 2, or 3. So my acceleration at 9 hours would be 3. So from there I can conclude that this is the time where the acceleration would be the greatest. So the acceleration is the greatest at t equals 9 hours. All right, let's take a look at the next one. Okay, and then part C is asking us over what time intervals from 0 to 11 is the particle moving to the left. And as we know from before, moving to the left is equivalent to asking where is the velocity negative. And remember, what we have up here is the graph of velocity. So if you look at this graph, where is this graph literally living in the negative area, in the negative land? And that looks like it's happening over these time intervals. So it looks like the velocity is negative from 4 to 10. Okay, so the particle is moving to the left over the time interval 4 to 10 because v of t is negative. And then the next question here asks us something that's actually a lot different. And just on a first reading, you might think that it's not that much different. It's asking us, where is the velocity of the particle increasing? So this is not asking us, where is the velocity positive? This is asking us, where is the actual velocity of the particle increasing? Or where is the slope of velocity positive? Or if you really want to, where's the acceleration positive? So those are the things that we're looking for. We have the graph of velocity up here. And what we're trying to answer now is, where is this graph increasing? So when I look at this graph for increasing, I see an increasing section from 0 up to 2. And again, I can comfortably say that because it looks like my slopes here are positive from 0 to 2. The slope of velocity is positive over that time interval. And the slope of velocity is also positive, looks like from 8 all the way to 11. So the slope of velocity is positive, means that velocity is increasing. So it looks like I've got 2 time intervals there. 1 from 0 to 2, and 1 from 8 to 11. Those are my time intervals where velocity is increasing, or where acceleration is positive. So what I'm going to say is 0 to 2, and then 8 to 11 was, I believe, what the other one was. And I'm going to say velocity is increasing here because v prime, which is acceleration, is positive. Okay. Now E. E is again asking us a slightly different question, and it's different enough to make us have to really think about what's going on in that original velocity graph. So this is where the, not velocity, but the speed of the particle is increasing. Now, if you recall from our earlier discussions, the speed of a particle is increasing when velocity and acceleration have the same sign. So we want to look for spots where the velocity is positive and the acceleration is positive, or where the velocity is negative and the acceleration is negative. And as we look for this, I want you guys to remember that the acceleration is the same as the slope of velocity. So this is going to be kind of a brain bender. We're going to look up at the original velocity graph and look for places where the velocity is positive and the slope of velocity is positive, or where the velocity is negative and the slope of velocity is negative. I want these things to happen at the same time. All right, let's take a look up there. Okay. So just to make this cleaner, I'm going to erase everything that we started with up here. So let's make this graph a little cleaner. Okay. So let's write some things so we want to make some observations where the particle is speeding up. Okay. So again, I'm looking for where the velocity and the acceleration have the same sign, whether they're both positive or both negative. Okay. So I see that from 0 to 4, the velocity is positive, but only on a certain part of it is the velocity positive and the acceleration positive. That's this part right here. So for that particular interval, we see that the velocity is positive because we're living up here in positive space. And the acceleration is also positive because we see positive slopes over that interval. So I know that the particle is speeding up from 0 to 2. Going on the next interval from 2 to 4, I see that the velocity is positive still. The velocity is positive because this graph, which is a velocity graph, is above the x-axis. But the slope of this graph is negative, so that means the acceleration is negative. So this would not be an interval where the particle is speeding up. That would be one where it's slowing down. In the next interval, we'll say from 4 to 8. So what I see through this time interval is I see that the velocity is negative because this velocity graph is below the x-axis. And I also see that the slope over this interval is also negative. The acceleration is negative. So in that time interval, velocity and acceleration have the same sign. So I'm going to add this to our intervals. It looks like from 4 to 8. Okay, and then we're going to have a couple more intervals to check. If you want to, why don't you pause the video for a second and see if you can figure out where would be the last interval where the particle is speeding up. Okay, so the particle is actually speeding up as a last interval from 10 to 11, because this is the interval where the velocity is positive. The velocity is literally above the t-axis there. It lives in positive land. And the acceleration, or the slope of this line, is positive as well. So that's the last interval where the particle is speeding up, from 10 to 11. This part of the graph, the particle is actually slowing down because the velocity is negative, which means the particle is moving to the left, but the acceleration, or the slope, is positive. So you can kind of see here that the velocities are inching closer towards 0. And when they're doing that, that means that the particle is speeding up. Whereas in this last part, you see how the velocities are branching away from 0 and going up and more positive. That means that they're speeding up. All right, so those are our 3 intervals: 0 to 2, 4 to 8, and 10 to 11. 0 to 2, 4 to 8, and 10 to 11. And again, this is because, and this oftentimes is the most important part of writing these, because I want you to be able to communicate effectively what the reason for your answer is. And that's because both velocity and acceleration have the same sign, positive and positive, or negative and negative, remembering that acceleration is the slope of v of t, the slope of velocity. Okay, and then in part F, at what times is the acceleration of the particle undefined? So the acceleration, again, is the slope of velocity. So we're looking for where the velocity, the slope of velocity is undefined. That's basically going to be places where we have points of discontinuity, or points of vertical tangent lines, or any cusps. And you can see that there are certainly a few of those up in that velocity graph. If we zoom up there, we've got, looks like a cusp at 4, a cusp at 8 are our 2 primary places where the slope is undefined. So we would say at t equals 4 and t equals 8, the acceleration is undefined. All right. And then this last part right here is really stretching us into the next idea that we're going to explore later in the winter. So what I'm going to do here is just basically talk about this and talk about what you would do. So the area of the semicircle on the interval 0 to 4, and if you look at that graph in front of you, the area of the semicircle, which I'm going to call A1, because the semicircle has radius 2, our area of that would be pi times 2 squared, and because it's a semicircle, we take half of that, and that would give me 2 pi. And then if we take a look at the area of the triangle on the interval 4 to 10, I'm going to call that area 2. So for that triangle, we've got an area where we find 1/2 the base and the height. And the base goes from 4 to 10, so that's 6. The height goes all the way down to -6, so the height is 6 as well. And then we take half of that for a triangle. And we would end up with 6 times 6 is 36. Take half of that is 18. And area 3 would be that last triangle from 10 to 11. And again, we've got a base of 1 and a height of 3. And multiply by 1/2. So that gives us 1.5. Okay. Now, each of these things, what we are basically doing is multiplying two different quantities. In order to find area, what we're doing is multiplying the quantity of the y-axis, and the y-axis is measured in miles per hour. So that's the y's, and we're multiplying that by the thing that we got on the t-axis, or the x-axis, and that was measured in hours. Because remember, this graph up here is a velocity versus time graph, so the y's are measured in miles per hour, and then the x's, or the t's, are measured in hours. So our area is miles per hour times hours. And if we multiply those units together, we just end up with miles. So we see this relationship here that the area underneath these shapes would give us the number of miles traveled. And that is what all these areas added together means. If you were to add all these things together, what we would end up with is the total distance traveled by the particle. But like I said, that is an idea that we will be exploring in a much deeper level later on in this winter. Okay, in this problem, again, what we're given is we're given a velocity graph. So the velocity is measured in feet per second. And we're asked a few questions, probably about velocity and acceleration and possibly distance traveled and things like that. So let's take a look at the first one. On what open intervals or at what times from 0 to 6 is the particle at rest? So at rest means that we're looking for places where the velocity is equal to 0. And because this is the velocity graph up here, we're just looking for places where this graph is equal to 0. And I can see two places, one right there at 1, and then one right there. We'll call that 4.2. I don't think that it's really worthwhile to find exactly what that point is. So we'll say t equals 1 and t equals 4.2. And we picked out both of those places because those places are where the velocity is equal to 0. And again, this is the graph of velocity, so we want to look for where this graph literally is 0. Not positive or negative, but 0. The next question asks us to find on what open intervals is the particle moving to the right. This is where the velocity, if you remember, needs to be positive. So if we look up at our graph here, we're trying to look for places where the velocity is positive. And I see this section of the graph, Remember, this is a velocity graph. This section of the graph, my velocity graph, is negative because it's below the t-axis. This section of the graph, the velocity graph, is positive because the velocity is above the t-axis. It lives in positive land. So we are going to write one interval would be from 0 to 1. And then I've got one more interval as well over here. That would be, it looks like, from 4.2 to 6. And our reason for that is because those are the places where the velocity is positive. All right. Remember that when we look for this, we're not looking for where the slope of this graph is positive, but because this is the graph of velocity, I can't say that enough, this is the graph of velocity, we're looking at where the graph is above in this area right there, above the t-axis in positive land. Okay. On what open intervals or times is the particle moving at its greatest speed? So remember, speed is the absolute value of velocity. So we're looking for where the absolute value of velocity is the greatest. So we don't care whether velocity is positive or negative. We just want the all-out largest number. So if I look up at my velocity graph here, I see the largest positive velocity we get is 4. But then the largest negative velocity we get is negative 6. So then I would conclude, that the greatest speed would be 6. And that happens at t equals 3. That's where the velocity is negative 6. And that just means the particle is moving to the left. So I would say that the greatest speed is 6 feet per second, at time t equals 3. And we've got the second part here, the greatest velocity. Velocity is not the same as speed. Velocity is asking you to find where this graph has the highest velocity, and I can see a velocity of 4 right there and a velocity of 4 on this interval as well. So I'm going to name those places. I hit a velocity of 4 at t equals 0, and then we had the interval up here went from about 5 to 6. Okay. And the next question asks us to find where the particle's speed is increasing, where this particle's speed is decreasing. Recall from previous questions that speed increases when the velocity and acceleration have the same sign, either both positive or both negative, and speed is decreasing when the velocity and the acceleration have different signs. One is positive, one is negative, or the other is negative, the other is positive. So let's find first where the speed is increasing. So looking at the graph, we want to look for where velocity and acceleration are both positive or both negative. Remembering that this, again, is the velocity graph. So in this stretch, I see that my velocity is positive because the velocity is in this positive territory, but its slope, the acceleration, is negative. So here I would say that that is a region where the speed is decreasing. So the speed is decreasing from 0 to 1. Because that's where the velocity is positive. So the velocity is positive up here. But the acceleration is negative. And on the next region, I see that here my velocity is negative because it's below the x-axis, and the acceleration is negative as well because the acceleration is the slope of velocity. And I actually see that again right there. Negative velocity and negative slope. So I'm going to record those as both speed increasing. So I would say from 1 to, oops, I forgot already, 1 to 2, and from 2 to 3. Again, because both the velocity and the acceleration are negative, that means a particle is heading in the leftward direction. So it's a leftward velocity and a leftward acceleration. The overall speed is increasing in the leftward direction over those intervals. Okay, the next part, right there, we still see that our velocity is negative, but because the slopes of this graph are positive, we know that the acceleration is positive. So this is yet another interval where the particle is slowing down, where the speed is decreasing. And that would be from 3 to 4.2 is what we called it. That's right, 4.2. Fantastic. And then I think we've got one more interval to take a look at here. This interval, we see that the velocity is positive because, again, our velocity graph is above the t-axis, and then our slope, which is acceleration, is positive as well. So I would say that the speed is also increasing from 4.2 to 5. And then let me just talk about this last interval right there. This last interval, yes, the velocity is positive because this stretch of graph lives in the positive space. But the acceleration there is equal to 0 because the slope over that interval is 0. So this particle would neither be speeding up nor slowing down. It's just a constant positive velocity from 5 to 6. As a matter of fact, the constant positive velocity is just 4 over that interval. So if the particle is keeping a velocity of 4 from 5 to 6 seconds, then it's neither speeding up or slowing down. The velocity is staying constant. Okay. Question E asks us what the particle's acceleration would be at 4.8 seconds. So let's take a look up at the graph. 4.8 seconds would put us at about that point right there. So because we're looking for acceleration, we want to know the slope at this point to find the acceleration at 4.8 seconds. And what we can do is take a look at the slope between the 2 points given to us. We see that one point would be 3, negative 6 on one end of that line, and the other point up here would be 5, 4 on the other end of that line. So we can find the slope between those 2 points by going 4 minus negative 6 over, and then 5 minus 3. We'd end up with 10 over 2, which is 5. So my acceleration at 4.8 seconds would be 5 feet per second per second. So I'm going to record that down here. The acceleration at 4.8 seconds is 5 feet per second per second. And what this number means is that the velocity is increasing at a rate of 5 feet per second when t equals 4.8. Okay. And then on what open intervals or what times from 0 to 6, is the acceleration the greatest? And remember what we've been talking about so far. The acceleration of a particle is the slope of its velocity. So we want to look for here, where is the slope of velocity at its greatest? So if we zoom up to the graph, what I see are some negative slopes over here, and I see positive slopes right there, and 0 slopes right there. So the acceleration or the slope of this velocity graph would have to be the greatest when the slope is positive. If there's only one spot or one interval where the slope is positive, and that occurs from 3 to 5. That's the only spot where the acceleration is positive, so therefore that's the only spot where the acceleration is the greatest. So we would say the acceleration is the greatest from 3, whoops, I wrote a 2. From 3 to 5. Okay, and then for this last problem, what is the particle's displacement during the first 2 seconds? I'm not going to explain this step by step, but I am going to give you a hint. Look at the area from 0 to 1 and the area from 1 to 2, and then think about this. That would give me the distance traveled, because the velocity is positive there. That would be the distance traveled to the right, and this would be the distance traveled to the left. So then I want you to think about what the displacement would have to be, just considering those 2 facts. We see, all right, on the last page here, we are given a few problems. All right, let's take a look at the first one and read it. We got 2 runners, runner A and runner B, that run on a straight race track for 10 seconds from 0 to 10. So the graph above, which consists of 2 line segments, shows the velocity, meters per second, of runner A. And the velocity of runner B is given by this function written down here. V of t equals 24t over 2t plus 3. What a great function that is. And then in A, we're asked to find the velocity of runner A and the velocity of runner B at time t equals 2 seconds. So let's find the velocity of runner A at t equals 2 seconds. Luckily for us, the velocity of runner A is given by this graph over there. This is a velocity graph, so we can just look at t equals 2 seconds and find out that our velocity there would be, well, what you can do is you can find the slope of the line. This line looks like it goes over 3 and up 10. So the slope of this line would be 10/3, or 3.3 repeating. And that means that for every 1 unit we go over, we'll go up 3.3 repeating. So then the velocity at time 2 would be 6.6 repeating. So the velocity at time 2 of runner A is 6.6 repeating meters per second. And then the velocity of runner B is found by using this equation that we're given. We're given 24t over 2t plus 3 and told that that is the velocity of runner B. So we can just plug time 2 in for t. 24 times 2 is 48. And then 2 times 2 is 4. 4 plus 3 is 7. So 48 divided by 7, I'm going to reach for a calculator there, is 6.857. So those are our two velocities of the runners. The next question in B is asking us to find the acceleration of runner A and the acceleration of runner B at 2 seconds. Remember that acceleration is equal to the derivative of velocity, and that's the slope of velocity. So what we're going to do is find the slope of this graph up there to find the acceleration of runner A at time t equals 2 seconds. And the acceleration of runner A at time t equals 2 seconds is the slope of this graph at t equals 2, and we found that up there from the previous example. 3.3 repeating because we see that the line goes over 3 and up 10, so 10 divided by 3, and we get 3.3. And that would be measured in meters per second. And the acceleration of runner B is a little more complicated. What we're going to do is, because we're given an equation for the velocity of runner B, to find the acceleration of runner B, we're going to take the derivative of that equation. And we need to use the quotient rule here. So we've got low d high minus high d low all over low low. So if we were to simplify that out, we'd end up with 48t plus 72 minus, and then 48t all over 2t plus 3 squared. And those 48t's are going to cancel out. And from there, if we find the acceleration at time 2, by just plugging in 2, we'll get 72 divided by, and then we'd have 7 squared, 72 divided by 49, which is 1.46 meters per second. All right, let's take a look at the next one. Okay, this question is asking us which graph best represents the position of a particle. This is asking us which graph best represents the position of a particle, s of t. So notice that each one of these graphs is a position graph, s of t. They're not velocity graphs, they're position graphs. And then we're given some information about the velocity and the acceleration. We're given that the acceleration is positive and the velocity is positive. Now, in order to deal with this, remember that the velocity is the slope of position and acceleration is the second derivative of position. So what that means is we're trying to look on these graphs for places where not only is the slope positive, so the slope of the position is positive, but we want the slope of the slope to be positive as well, or we want the slope to be increasing over time. Or another way to see it is we want s of t to be concave up. If the second derivative of s is positive, so if the second derivative of s is positive, that means that our original function s is concave up. And if we go through in each one of these examples, we see that in A, yes, the slope of s is positive, so velocity would be positive here, but the acceleration would be 0 because this graph is neither concave up or concave down. It's just a straight line. In part B, we see some positive slopes again. So the velocity would be positive in this position graph, but the acceleration would be negative because those slopes, those velocities are actually decreasing as you go towards the right. Or you see the position graph is concave down. We're going to skip C for a second, and I bet you probably know why, and look at D. In D, you can see part of this position graph has really steep negative slopes, so that would mean that the velocity is negative, so we don't want D. And then if we look at E as well, we see some negative slopes on here, which means that the velocity would be negative at those times, and we can cross out E from that as well. So that leaves C. C is where the velocity or the slopes of position are positive, and we see that the velocity is increasing as you go from left to right. The slopes are increasing. We see the graph is concave up. So this means that the acceleration is positive as well. Okay. And then in this last question here, we're given the graph of the velocity of a car traveling on a straight road from time 0 to 50 seconds. And we're given a graph of velocity, and a table with velocity as well. And in part A, we're asked during what intervals of time is the acceleration of the car positive? Remember that the acceleration is the derivative of velocity, so we're being asked here, where is the derivative positive? Where is the slope of velocity positive? And if we look at our graph, we see positive slopes right there, 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 right up. And then we see some negative slopes, but we go back to positive slopes along that interval. So we can safely say that the acceleration is positive over the intervals 0 to 35 and 45 to 50. Let me write that neater. 45 to 50. Because the acceleration is equal to the slope of velocity. All right. In part B, we're asked to find the average acceleration of the car over the interval 0 to 50. So the average acceleration is found by looking at the change in velocity over that time interval. So we're going to do velocity at 50 seconds minus the velocity at 0 seconds over 50 minus 0. What's nice about this particular example is that you don't need to plug in any numbers into an equation or anything like that, because we've got a table up here that tells us certain velocities at certain points in time. So the velocity at 50 seconds is 72, and the velocity at 0 seconds is 0. So we're just going to write 72 minus 0 over 50. So then the average acceleration would be 72 feet per second over 50 seconds, which gives us 1.44 feet per second per second. Or feet per second squared. And our last part, find one approximation for the acceleration of the car at time t equals 40. So at time t equals 40 is right there, and because the acceleration is the slope, what I want to do is approximate the slope at t equals 40. So the approximate slope of velocity at t equals 40. So we're going to set up a few options that you could do. What you could do is you could find the slope between 35 and 40. You could find the approximate slope between 40 and 45, or you could also find the slope between 35 and 45. So let's just find the approximate acceleration. Excuse me, that's not the right way to write it. The approximate acceleration, which is the approximate slope of velocity at 40, which would be approximately equal to, and what I'm going to do is take a look at the slope between 35 and 40. So I would have 75 minus 81 over, so I'm getting those numbers from here, 75 minus 81 over 40 minus 35. Again, this is just the approximate slope. I have no way of knowing the actual slope at 40 because I don't have an equation, but we can approximate the slope by using values from the table. So that would give us negative 6 over 5, which is negative 1.2 feet per second per second. And remember that this acceleration tells us that velocity is decreasing. Because the acceleration is negative, the velocity would have to be decreasing. And you can see in our graph that at 40, you can very much see that velocity decrease at that point in time. Okay, that's it.